Thanks. It's nice to be here. I'd never been to Irvine before. It's really beautiful, so I'm very happy to be here. Thanks for the invitation. I asked him what I should talk about. He said methods in social epidemiology, so I have about 59 slides here of some ideas that I have about problems that we face mostly in social epidemiologic analysis. So I'm not going to talk too much about substantive concepts, more about analytic concepts and causal inference, and just some observations and pet peeves and things like that I have. So stop me at any point if you have a question as we go along, but I'll try to speak quickly so we can cover this in an hour. I'm not advancing. So,
point to the computer. Right?
To the computer? No. All right, I guess I'll advance from the screen. Okay, so here's an outline. This is okay. I can. All right. Technical problems. Oh, that's my talk, but I have it on the desktop, so I can take that out.
Okay, well, there's a pointer here too.
You know, it's linked, but it's not happening. Sorry.
That's okay. I'll advance from the screen.
Okay, yeah.
Okay. All right, so here's just an outline of the topics that I'll cover. I'll talk a little bit about sampling variability rituals, adjustment rituals, a graphical language for encoding what we know about the subject matter, confounding, how we can use the graph to define what's a confounder, selection bias, again, something we can read off the graph, and another threat to validity that doesn't get as much attention as confounding, but I'll show it can be very important, especially in life course studies. And I'll give an example. I'll invent a life course study versus a case control study, and then as a cohort study to make some observations about various things, positivity and then selection bias, and then warn you that, of course, it's just an abstraction. You shouldn't take it too seriously. So first about sampling variability. We have these rituals about variability, and I've just copied the Wikipedia definition for ritual here so you can see how it maps to the way that we treat things like confidence intervals and p-values. Because the purpose of the ritual, back in the prehistory somewhere, there was some real reason why we did this thing, but we've kind of forgotten about this reason now. So we just do it now habitually because it's the practice of our tribe to do it this way. And it strengthens our social bonds. It demonstrates respect or submission. We go to the epi meeting with our small p-values and try to impress each other that my p-value is smaller than your p-value. And this gives us a sense of social acceptance, approval for some event, sometimes just for the pleasure of the small p-value itself. So we don't often remember the origins of these things or why we do them, but they've just become rituals for us. So let me give an example here. Here's a social epi paper by a good group from Michigan, Jim House and others. And here they're looking at a hazard ratio of mortality associated with race and sex, whether you live in a city or a suburb or a small town. And the top panel is younger people, and bottom panel is older people. So I'll just focus on this one estimate here. This is a hazard ratio of 3.18 if you're a black male living in the city compared to and you're 65 years or older. So what is the meaning of this estimate, right? So data were a stratified probability sample, so it says something about the population, the whole population of the United States that it came from. So the implication is that there's some parameter out there in the real world, some number in the population, and we want to know what that is by taking this small sample. So we grabbed a handful of people, 3,600 of them, and we're making some estimate there. And the sampling variability ritual, this p-value or confidence interval, is a way of linking the small group of people we have to the population that they came from. So this value that we have is the estimate of the population value, and we have to believe if we're going to report that point estimate and the p-value, then we're saying that the only threat to validity there is the sampling variability. That is that this number that we get might not be the real number because it might vary because of the particular group of people that I grabbed a hold of, but that there's no other reason why it differs. It's not any measurement error, no misclassification, selection bias, anything like that. So, whoops, how do so this all-cause mortality hazard rate for this time period in this group of people is 3.18. So we know what this means, that their hazard rate is 3.18 times higher than for the reference group. and the 95% confidence interval is some number, which is also part of our reporting for the sampling variability. So the first question is, what does the confidence interval mean? The most common answer I get when I ask my students that question is the wrong answer. There's a 95% chance that the true value is in this interval, 177 to 572. And that's the wrong answer because it's the interval itself that's the random thing. Right? Every time in the frequentist model that I'm using here, every time I draw that group of people from my sample, from the population into my sample, I grab a different group of people, and every time I do that, I construct a confidence interval, and every time I do that, I get a different set of limits. So the confidence interval is moving around. The true value in the population doesn't move around at all. So you can't say that there's a 95% chance that something that's fixed that doesn't move is in that interval, because the interval is already drawn. Once you've randomly selected, all the randomness is gone. That interval is what it is, and the true value is either inside or it's outside. So as a frequentist, you can't say that there's a 95% chance that it's in there. Now, if you're Bayesian, you could say that, but then you have to have a prior probability, and you have to know something about the subject matter, and then those two are not going to line up. It would only line up if you had a flat prior, if you were completely ignorant. And if you were completely ignorant, you wouldn't be an epidemiologist, you'd be a biostatistician or something. So the punchline here, or the bottom line, is that there is no, if you're using the frequentist definitions, there is no real definition for that particular interval. You can't tell anybody what that thing is. All you can tell them is that it's one member of a family of intervals that you would get if you did this over and over and over again. And that family of intervals has a characteristic that 95% of them cover the true value. But the one interval that you have, you can't really say anything about it whatsoever. So given that we all do studies one time and not a whole bunch of times, this one particular interval that we have doesn't actually have any real meaning for us. Now, it's still useful as some measure, some vague measure of precision. If it's a wide interval, that's worse than if it's a narrow interval. So we can still compare our intervals and say, oh, mine's narrower than yours, that's better. But these particular numbers, they're not 95 of anything. They don't really have any, they don't have any formal interpretation. I'm not trying to convince you to report p-values instead of confidence intervals. That would be even worse. But I'm just making a point about the fact that we report this as a ritual, even though it doesn't, for us, it doesn't really have any meaning anymore. Here's another example. This is a paper from Christenfeld. They looked at the toxic exposure to New York City. Apparently, if you were a resident in New York City, you had an ischemic heart disease mortality rate that's 50% higher than other people, including residents of other people in the United States. And you also have an elevated ischemic heart disease mortality rate if you're a visitor to New York City. But if you're a resident in New York City and you were someplace else, then you had a lower than expected rate. So this finding gives this ratio of ischemic heart disease mortality rates for these different groups. And the ratio for residents of New York City is 155.8. And it also has a confidence interval. So we could ask the same questions about this. We can define in time who we're talking about here. This is actually based on all deaths in the United States from the decade 85 to 94. We're interested in people in New York City compared to people from other places and comparing their ischemic heart disease rates. So there's a true value in the population. We grab a sample, we look at the value in the sample, and we connect that sample to the rest of the population using these rituals like p-values and confidence intervals. So again, we have to assume that there's no reason why we get a different number except for the sampling variability, right? So there's no misclassification, no selection bias, so forth. So if we take that one estimate, what does that confidence interval mean there? That goes 155.2 to 156.5. What's the meaning of that interval? Well, the thing is, this is based on all the data in the United States, right? It's based on all deaths during that time period in the United States. So when we grabbed a handful of people into our sample, we took all of them, which means that if we did it again and again and again, we would get exactly the same number every time. There's actually no sampling here. So to say that there's an interval that goes from 155.2 to 156.5 is ridiculous, because every time we would do this study, we would get 155.8 every single time. So the real confidence interval goes from 155.8 to 155.8. There's no sampling variability whatsoever because there's no sampling. We take 100% of the sample every time. Why did they report this interval? Because it's a ritual, because the journal expects confidence intervals, right? It's based on the idea of sampling, which didn't actually apply in this situation, but we did it ritualistically, right? So p-values and confidence intervals link a population to a sample. If there's no sampling, then they don't really have any meaning. Like, they're not really the appropriate tool anymore. But they're still necessary for us ritualistically because we're not going to get published if we don't have them. There are many situations where we don't actually have sampling. For example, when the data are completely enumerated, so I gave that example with the Christenfeld paper, or when data are not sampled from an identifiable target population, like Nurses' Health Study. Hundreds and hundreds of papers every year from the Nurses' Health Study. They all have p-values and confidence intervals, but the Nurses' Health Study is not a sample of nurses. It's not nurses are not a sample of Americans. Like, there's no sampling going on there at all. So it doesn't make any sense. The p-value doesn't have any meaning whatsoever. Or the Framingham study, from which we know most of what we know about cardiovascular disease. Again, it's not a sample. Framingham is not a sample of US cities, or it's not a sample of anything. It's Framingham. So these things exist as a ritual. They don't actually have any formal definition. All right, let's move on to adjustment rituals. So I start out with this quote from a 19th century social epidemiologist. Philosophers have only interpreted the world. The point, however, is to change it. Because the idea of etiologic research is about what would happen if we changed the world, if we changed something, if we intervened in some way. So there's two flavors of epidemiology. You can be doing surveillance, in which you want to describe the world, right? So if you do surveillance, you want to answer some question like, what's the number of people who are HIV positive in a particular place at a particular time, right? That's a real number for a real number of people, and it's descriptive. So you don't adjust that for anything. Like, the number of people who are HIV positive is the number of people. Like, you just want to count those people up and say, this is the number. That's surveillance, and it's really important in epidemiology and public health, so we want to do surveillance. But then we don't adjust for anything, right? So all these techniques we learn about for adjusting for confounding, that doesn't apply to surveillance. It applies to the other kind of research, which is etiologic research. The etiologic research is all about, if I did one thing versus doing another, how would this outcome parameter, this frequency measure, whatever it is of disease, how would that change? So whenever I'm changing the world, like in the quote, then I'm interested in etiologic research. Why do I adjust for things? Because I'm not actually changing the world, right? I'm doing a pretend thing. I'm hypothesizing what would happen if I changed something. How would this frequency measure change? So hypothetically, it's this new number, and I'm making a contrast. And that's why I do adjustment, because I only have observed data where I'm not actually intervening on anything. So I'm estimating what would happen if I did intervene, right? So that's why we adjust for things. So we observe, I'll use the pointer now. We get to observe the outcome distribution given some categories. Like, we might know the lung cancer rate among smokers. We might know the lung cancer rate among non-smokers. So we observe some conditional distribution. What we actually want to know is what would be your lung cancer risk or your lung cancer occurrence if I force you to smoke versus if I force you not to smoke. Now, as epidemiologists, we don't get to force people to smoke. And unfortunately, we don't get to force people not to smoke. So we have to use observed data. And the threat is always that there's some variable sitting out there that is causally, it's one of the causes of why people smoke. And if that also happens to be a cause of lung cancer, then when we look at this association between X and Y in our data, it's not going to be the causal association. It's not going to be what we would get if we actually made you smoke versus made you not smoke. So there are rules for how we transform the observed quantities into the thing that we want. They're not equal, but if we condition statistically in some way, this is why we adjust for things. If we condition in some way, there's a theory about how we connect the thing that we want about intervention, how we get that from the things that we can observe from the data passively. And they're based on these kinds of structures, which leads me to the next point about this language, this graphical language for how we represent those structures, how we communicate those to people. We always make these contrasts. What would happen if we did thing one versus thing two, right? So when I see an expression like this, like the outcome distribution given that I set you to different levels of smoking, say, what I'm really interested in some contrast. Like, what if I set you to smoke versus if I set you to not smoke, right? So I define what those two levels are that I'm interested in, and then I look at how the distribution of lung cancer would change between those two worlds where I'm making this hypothetical intervention. So if you think about that as the contrast, what you want to know when you estimate this thing, you clearly don't want to adjust for anything that is on the pathway or is that affected by the thing that you're moving around. Like the thing that you're changing here, X, you're assigning it to be x1 or x2, if anything follows as a consequence from that, you don't want to adjust for that because that's part of the mechanism by which you're having the effect that you're having, right? That's part of what you're doing when you manipulate people. So you don't want to touch those things. You don't want to mess around with those things. So for example, suppose I wanted to know if a cigarette tax affected lung cancer mortality, right? I have in my data set cigarette consumption. That's something that's sitting in my data set, so I might as well adjust for it, right? Because I've measured it, right? But that would be a really bad idea because the cigarette tax has its effect by affecting cigarette consumption, which has its effect on lung cancer mortality. So if I put my thumb on Z here, if I hold it down so it can't move, right, then it looks like cigarette tax has no effect whatsoever. It does really have an effect. It's just that it goes through the thing that I held constant. So I never want to adjust for a thing like Z. That would be a really bad idea. I would get the wrong answer, right? Because I'm adjusting away the thing that I'm trying to discover, right? So that's a no-no. That's a bad idea. Now let's go back to this House paper. When they did this comparison, they did adjust for stuff. So they're not doing surveillance here, right? They must be doing etiologic research because otherwise they wouldn't have adjusted for these things: education, income, marital status, and health. Okay, so when they say that the mortality rate for black males here is 3.18 times higher, adjusted for a bunch of other stuff, right? So we're not in the surveillance world. We're not talking about the real world. We're talking about what would happen in a world in which blacks and whites and men and women were balanced on education, income, marital status, and health, right? So it's clearly not a descriptive study. Otherwise, it would be unadjusted. It's a little bit hard to think about this setting, right? Setting people to be black men versus white women, because we don't really have a way of turning black men into white women and things like that. So it's a little bit obscure what we mean by that contrast. But anyway we look at it, it looks pretty clear like this vector of things that they adjusted for, education, income, marital status, and health, is probably somewhere between the exposure and the outcome. Like it's one of those Z things that you probably shouldn't touch because you're probably adjusting away part of the pathway by which those things have their effect, right? They're probably more affected by exposure than they are confounders of the exposure. I don't know exactly what the causal structure is because I'm not a sociologist, but it probably looks something like this. You know that your race, your sex, your residence have some influence on what kind of education you get, on what kind of income you get, on who you end up marrying, and then these things all contribute to what your health status is going to be. And most people on their way to dying get sick first, right? It is possible to just be fine and then you get hit by a bus and you're dead, but most people get sick and then they die. So you have to think that bad health is on the pathway. So when they adjusted for bad health, they adjusted away a lot of the stuff that they were actually looking for. So that was a really bad idea. So you can be pretty sure that they got the wrong answer by adjusting for these things that are actually part of the mechanism that they wanted to uncover. So this, I'm not picking on these people because they're famous social epidemiologists. Like it's a good paper, but I'm saying as an adjustment ritual in our field, this is really crazy. It really doesn't make any sense because it's not surveillance and it's not etiology for the thing you actually want to find out about. So it's kind of bizarre that this is the way we do things. So I may not be exactly right about this structure, but I think the covariates that are adjusted for in the published analysis are primarily intermediates. And therefore, there's really no good theoretical reason why you should be adjusting for things. Now, you also have this problem because you don't really know how you're manipulating across race and gender. So it's a little bit obscure what the causal definition is here anyway. But this makes the decision about what's a confounder even more complicated. So we need some kind of a set of rules. We need some kind of a structure to define what's a confounder. How would we find these things? We need some kind of encoding of subject matter to know what would be a legitimate confounder and what wouldn't. And the system that's kind of taken over in epidemiology now in the last 15 years or so is this one developed by Judea Pearl, who's a computer scientist at UCLA, and described in his book, Causality. This is the second edition in 2009. These are non-parametric structural equations models that he develops as graphical tools, basically to help you identify confounding. So you can see where there are threats to causal inference in the observed data. And these are, they have a direct mathematical interpretation. So you just read things off the graph. These arrows represent functions that are not, they're not parameterized. So they can be any function. You don't have to say what that function is. It's not like in sociology where you say these things are all linear or something like that and normally distributed with normally distributed errors. We're much more cautious and conservative than sociologists. So we don't want to put any distributions on these things. We just say that they're linked in this way, that y is some function of x and z and its own individual error term. But this tells us something about the structure, the causal structure that we're dealing with. And it's a much less rigid statement than something like logistic regression that has this very rigid model form. So if you look at logistic regression, it says that all these log odds fall exactly on a straight line. There's no statement like that here. We're not making any parametric assumptions whatsoever. And that these things, x and z here are going to interact exactly multiplicatively. So the joint effects are set. We know what this distribution here is. The whole thing is rigid. Whereas in this model, we're not making any assumptions like that except for what's a function of what. But it still works to tell us where there's confounding. At the same time that it's not as rigid as a parametric model like logistic, it actually includes more information. So if I happen to know, for example, that like z causes x, and it's not the case that x causes z. Like suppose z is gender and x is smoking. Right? I know that being one gender or another can affect your probability of smoking, but I know that no matter how much I smoke, it's not going to change my gender. Like these are substantive things that I actually know something about, and I can encode that in a non-parametric structural equations model like this, in what I call a DAG, directed acyclic graph. But there's no way that I can tell a regression model that. Right? I can't tell logistic regression that x and z have this particular relationship. They're just on the right-hand side of the model. They don't know anything about how they're ordered causally. So this leads to a precise definition of confounding. So if I want to know about confounding, I can represent it in a model like this, and a confounder is going to be something that sits up above the exposure and the outcome, that affects the exposure and affects the outcome. So I get this pattern that I can detect in the graph, which is this unblocked backdoor path. Right? It's called a backdoor path because the arrow goes into my exposure, and it's unblocked because there's no adjustment or collider on that path. And I'll show you examples of those in a minute. So for these causal effects, this is kind of what I told you before. I want to make some contrast between what would happen if I set the exposure to one level versus set to another level. And I just want to know if that contrast is off the null. Like if setting you to smoke minus setting you to not smoke, the outcome risk that you would have for lung cancer, if that's not 0, then I know that smoking has a causal effect on lung cancer. Right? And I could do that as a difference. I could do it as a ratio. I could take any contrast that I want of those two interventions. So confounding represents the distinction between the observed data and the causal estimate. So Pearl's definition for confounding, which I think is a helpful one, is that it's when the distribution that you observe of the outcome, conditional on the exposure, or conditional on some whatever additional covariates you might be interested in, is different from what you would get if you set people. So if I force you to smoke versus force you not to smoke, I would get a difference in your risk of lung cancer. Is that the same as observing the smokers and the non-smokers? If it's the same, then there's no confounding there. But in many cases, it's going to be different because of the reasons why people are smoking. And that's when I have to adjust for things, condition on additional things to break this backdoor path. So this is just an example from a tutorial by Greenland. And the backdoor paths are the ones that, as I say, have arrowheads going into x. And I can follow that back in some way to get back to my outcome y. So I mentioned a collider. A collider is any path where I enter and exit through an arrowhead, through arrowheads here. So on the path x, a, c, b, y, I go into C and I leave C through arrowheads. So C is a collider on that path. So there's actually no confounding on that particular path. Any path that has a collider on it, I don't get any confounding on that path. But I do have confounding from things like XAUY, or XCBY, or XACY. Those are all confounding paths. So I have to block all those by adjusting. I don't have to block XACBY because C is a collider on that path. So these are the rules. You can read it in Pearl's book, and there are many epi papers now that describe these. But an interesting realization, and Pearl only came up with this in the 90s. It entered epidemiology in the late 90s, really caught on in the last decade. And it's kind of crazy that there are some very basic observations that we never really noticed before in epidemiology until we had these DAGs. So one of them is that anytime you have two variables that are independent in the population, so say take x and b here, this inverted capital pi means they're statistically independent. So probability of x given b is the same as the marginal probability of x. Okay, so I don't know anything about these two things. Like, you know, if I know something about x, it doesn't tell me about b. If I know something about b, it doesn't tell me about x. But they're both parents of c, right? They're both ways that you can get to c. When I look within strata of c, those things will be correlated. Okay, so it's because if you didn't get there by one path, you were more likely to get there by the other path. Like, say there are two ways that I could get invited to speak at University of California at Irvine. One was by being smart, or the other is by being handsome. So I walk in the door and you say, oh, that guy must be smart, right? So it's because being smart and being handsome might be independent of the population. When you know one, you don't know anything about the other. But given that they're both ways to get invited to Irvine, if I didn't get there by being one, I was more likely to get there by being the other. So this is a general phenomenon. It means that when we adjust for things like C, we create correlations in the data that weren't there before. And we can actually create confounding that wasn't there before. So this was a relatively new revelation in epidemiology, that like there was an old idea in economics, sociology, that the more things you adjusted for, the better. You know, this everything but the kitchen sink approach. Like if I have 8,000 things that I measured here, I better adjust for all those, and then my result is really robust. But it turned out that Pearl discovered that a lot of things you're adjusting for, you're actually creating more confounding. You're actually opening up backdoor paths that weren't there before and leading to more bias in your data. And this has been a controversial idea. There's some people who still don't really accept this. Here's an example of a graph like that in a chapter by Maria Gleamore, where she's showing an example in substantive terms where you might have a structure like this, and you might adjust for this variable, and you create this confounding. And so they call this an M diagram because of the shape. So there's some people like Don Rubin at Harvard who argues that, you know, if I have a lot of covariates, I'm probably going to adjust for these things as well. And so I'm going to get rid of this. Whatever bias I create, I'm going to get rid of it at the same time because I have all these other variables as well. And then Pearl, in this exchange of letters, Pearl is arguing against this, saying, you really don't know what you're going to have and what you're not going to have. You couldn't say that as a general rule. So there's some controversy about how bad this can be, these correlations that we create. But there's some nice examples in the literature of a general problem like this around selection bias that I think illustrate how bad it can be. So it was in 2004 that Miguel Hernan at Harvard realized that a lot of things in epidemiology that we called selection bias, various kinds of bias that had people's names, like Bergson's bias and things like that, all had a common form, which was that they resulted from conditioning on some child of the exposure and the outcome, right? So this is my exposure, this is the outcome I'm studying, and somehow in the design or the analysis, I'm conditioning on something that's affected by both of those. And that when I do, I create that correlation between the two parents of that child in the way that I just described to you, and that bias underlies all the selection biases that we talk about in the literature. And when they did that, they solved a bunch of long-standing mysteries in epidemiology that had this kind of form. So one of them is the birth weight paradox, which has been around for 20 or 30 years. People have noticed that for a bunch of different variables, so smoking was one of them, black race was one of them, if you looked at the distribution of birth weights, for the smokers, for example, or for mothers of black race, the birth weight distribution was shifted lower, right? So mothers had birth weights that were systematically lower than mothers who smoked had birth weights that were systematically lower than mothers who didn't smoke, right? But if you looked at the mortality, infant mortality, why do we care about low birth weight? Because it increases risk of infant mortality. If you look at the risk of infant mortality across the range of birth weights here, you see that the smoker and non-smoker curves cross. It looks like it's just crossing a little bit, but this is because it's log scale here. This is actually a big difference up here. You know, like it's as big as this difference. It's just collapsed because of the log scale. So it's bad to be the child of a smoker, right? Because you're more likely to be low birth weight. But if you're going to be born low birth weight, it's better to be the child of a smoker, right? And it works for anything that lowers birth weight, like race as well, works in the same way. So you're more likely to be born low birth weight if you're black than if you're white. But if you're going to be born below birth weight, you're better off being a black kid than a white kid because your mortality rate is lower. And this was a mystery. People spent 20 years scratching their heads trying to figure out what was going on there. And they finally figured out after this Hernan paper about selection bias that it was exactly the graph that I just showed you, that what you had is smoking lowered birth weight, but you had some other things out there that were unmeasured that were much worse for you. Things like congenital abnormalities, birth defects, things that were really bad. Like smoking would take 50 or 100 grams off your birth weight. But if you had some kind of a birth defect, like it could kill you. It was really bad. So if you didn't get to this low birth weight by smoking, you were more likely to have this congenital abnormality. So smoking looks protective. If, in the birth weight equals 1 stratum, smoking ends up looking good because it's the best way to get there. It's the least bad way to get there. Right? And so they figured out this is exactly what was going on here. They solved this mystery based on these graphs that were just invented a short time ago. So we just noticed a similar pattern in a huge literature that exists around the so-called obesity paradox. So a bunch of clinicians have noticed, and there's a bunch of articles about this now saying, obesity is bad for you, but if you have heart failure, obesity is good for you. Like we look at the people with heart failure, and the obese people do better than the non-obese people. And we realized this is exactly the same graph. So we just published this letter. This is 2013. Yeah, so in May of this year, published this letter showing how you're doing the exact same thing. You're conditioning on getting sick here. Obesity makes you more likely to get sick, but there's other genetic, physiologic, health things that also contribute to getting sick. And you're creating this correlation with obesity that reverses the sign. So we had some simulations showing how easy it is to reverse that sign, resolving this problem. Obesity is not good for anybody, but it looks good because it's the least bad way to get heart failure, right? OK, I'm going to I have about 20 more minutes. I'm going to create a study here. I'm going to start it out as a case control study and then turn it into a cohort study to make a few points along the way, but mostly to show you the implications of selection bias that are even more profound or frightening. I'm going to go a little bit quickly here, but I can send my slides if you want to look through this in more detail so you can see how this works. I'm going to create a case control study here in a fictitious occupational cohort where you can be low, medium, or high occupation. Say it's like assistant, associate, or full professor. Like, there's 3 levels that you can be at. And I'll create these 10 trajectories. Like you could go through life full, 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 or assistant, assistant, assistant. So you could follow any trajectory there. I'll take 3 time periods throughout the life course. The outcome is something that, once it happens, you're done. What else? So low, medium, high. So there's 10. You'll see there's 10 trajectories here. And I set it up. I get to invent the data, so I can make it work out anyway. I've set it up so that your risk of the disease is just a function of how long you spend in a lower status compared to a higher status. So if you spend your whole life low, 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 you have the highest risk. If you spend your whole life high, 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 then you're at the lowest risk. So I can program that in. Now I'm going to do a case control study. I'm going to draw my controls at the beginning of the follow-up time as a random sample of the cohort at the beginning of follow-up time so that my odds ratio will be the same as the risk ratio. So here are my 10 trajectories. I'll put 1,000 people in each trajectory. These are all the possibilities of advancement that you can make throughout the life course. I think it's exhaustive, right? I mean, you can only go up. You can't be busted down from full professor down to assistant. No matter what you publish, you can never get demoted. And I set it up. I just use this formula here to set it up so that in this worst one, your risk is 50%. So I take these 1,000 people, and 510 of them are going to get the disease by the end. And in the lowest risk one, you only have a 5% risk, so only 55 people are going to get the disease. And I have my random 20% of these 1,000 people here as my controls. So I get time-specific risks of disease. Since it's a case control study, I'm actually doing this as the probability that you're exposed to low grade, given that you're a case or a control. Since in my sampling, I take an oversample of cases, basically. So I have to invert this conditional probability. It's how case control studies work. We get to study exposure as a function of case control status instead of the outcome as a function of exposure because we oversample. So I have these time-specific probabilities, and I can use these to construct any contrast that I want. Like I can use these to get at time 2 the odds ratio for the effect of well, it's going to be, for the probability of being low status given you're a case compared to the probability of low status given that you're a control, things like that. So I go ahead and construct these odds ratios or risk ratios from those numbers. I'll just use low and high here. I'll leave out the middle people for now just to be quick. And I can create these effect measures at each time period for the effect of being low versus high on mortality. And you see that, like I promised you, the odds ratio and the risk ratio end up being the same because of this design. If you sample your controls at the beginning of follow-up, you get the same thing. If you sample at the end of follow-up, you don't, which is the traditional way of doing things. And then there's a third way of doing case control studies, which is sampling each control at the time that the case occurs. It's called incidence density-based sampling. And then you get your odds ratio is the same as the hazard ratio. OK, so here are my effects. And you see they decrease over time on the ratio scale. And there's a bunch of studies, life course studies, that do this kind of thing. And they say, where in the life course does this socioeconomic factor have the largest effect? They say, oh, it's strongest when people are young. Right? But that's completely an artifact of what measure you're looking at. If I look at the risk difference, it's increasing over the life course. So the ratios are falling, the differences are increasing. So if I'd done a linear model instead of a logistic model, I would have gotten a completely different answer there. So that's the first thing to see, is these trajectories of the magnitude of the effect of the life course are arbitrary as a function of what scale you're using, what contrast measure you're using. Right? So be suspicious of that literature that looks where in the life course this thing has its biggest effect. OK, and then we have to think about what's the right answer, right? I want the causal effect of being in a particular occupational level, compared to being at a higher level at some time point. So I use some substitute population. I don't actually get to move people around. Like I don't get to change somebody's, change somebody from an assistant professor to a full professor. I have to use the observational data. So I find some substitute population of people who are like those people, but they're at a different occupational level as the substitute population. So I have this kind of substitution that I go through for the risk in a particular group of people. I need to find the unexposed people, and I need to find this substitute population that fills in for the risks that I would have observed in that people had they had a different exposure level. So, and then I can, at each time period, I can make that comparison. So let me take time 2 as my first example. I want the number of cases with low grade at time 2, so the proportion of cases with low grade at time 2, versus the proportion of cases with low grade at time 2 if I were to set those people to be high grade. If I just promoted all those people to full professor overnight, how would their risk of mortality change at time 2? Right? So it's clear where I get my low grade exposed people from at time 2. And I'm going to pick as my substitute population the people whose risk I'm going to use for the observed level. If I had made those people high, I'm going to use the people observed to be high there. Right? They're the people who are filling in for what would have happened to these low-grade people had they been high. Because it's a counterfactual contrast I'm making. I never get to see somebody in both levels, so I always need a substitute to fill in. Right? But the problem is there's actually 2 different kinds of people who are high at time 2. There's people who are high and they have the exact same history of occupation as the people that I'm substituting for. And there's people who have a different history. And when I computed those numbers before, I used all the high people. And what you see, in fact, is that they're confounded by their previous history of getting up to that point. Right? They're actually imbalanced on that history of what jobs they had. And so when I use them as a substitute, I actually get the wrong answer. Right? So I've changed, instead of getting a causal risk difference of 0.27, if I match them just on the people who have exactly the same exposure history as my exposed people here, to have high grade instead of low grade, but matched to their previous history, then I get a difference of 0.24 instead of 0.27. So they were confounded by their exposure history. If I do time 3, I get the same thing. Right? I want to know what would happen to these low-grade people at time 3. These are the only low-grade people at time 3. Had they been high-grade at time 3? Now, it's a little bit ambiguous. Right? I could mean had they been high-grade people at time 3, including all of the ways that people get to be high-grade at time 3. They're very different in their entire history. Or I could mean if I snap my fingers and they're automatically a full professor at this time with exactly the same history that they had before. So my causal question is actually a little bit ambiguous. It's not clear what I mean by that statement because I'm not really defining what the intervention is that I'm thinking about. So this is a lack of clarity that in the causal inference literature is called the consistency assumption, that to meet the consistency assumption, I have to tell you exactly how it is that I'm going to intervene on these people to change them. Since I didn't tell you that, you don't really know which is the right measure. So again, for the substitute population, I can pick these people that are matched exactly on their history, but a lot of the other people that are high have a different history, and so I get a different answer. If I use the full group of people that are high at that point, I have a bunch of other histories, and I get a confounded result. Right? So if I use this, if I think of my intervention as at the last minute, the last blip of time, I'm flipping these people to a higher level. I'll call that a minimum intervention strategy. Then I get a very different pattern of effects here across the life course. So now it's falling much more dramatically on the ratio scale, still rising on the difference scale, but I do have different numbers. But it's not clear that this is the right one and the other one is the wrong one. It depends on which intervention you meant. So when someone just writes a paper and says, here's the causal effect, it's X, right? That doesn't really tell you because there's several different ways you could get there, and you don't know which is the one you're actually trying to model. So you could think of the estimate being the always exposed versus the never exposed, conditioned on some previous exposure history, and then just flipping at the last moment, the last blip of exposure. You could have some other rule. So you have to be explicit about that to know which of these numbers is actually the one you want in the life course setting here. Now, there are techniques that match on exposure history, techniques like marginal structural models, that break up the time into chunks. And then within each chunk, you're matching, you're really standardizing at each time. And then conditional on that, you go on to the next time. And so these are techniques for getting this minimal intervention adjustment that I mentioned, where you take into account the time, you make sure everybody's matched at every time point. But the problem that arises from those kinds of models, as you'll see, is they create a certain kind of what we call a positivity violation, which means that they define contrasts that actually could not occur, right? They define causal contrasts where you could get a number, like you do the data analysis and you'll get a number, but that number actually defines people that couldn't exist, right? So let me take this example. Suppose I have this trajectory for medium, medium, high, and I say I want this contrast that's matched along the entire exposure history until that last moment. And then what if this person had been low, right? So I need to find people with this trajectory and match them to people with this trajectory and make that comparison to get the number. In a model, I'd be able to estimate that thing. But in fact, this is a trajectory, medium, medium, low, that can't happen because I told you that you can never be demoted, right? Once you get to be associate, they can't take that away from you again. So when you actually look in the data set, you'll see that there are no such people like that. So you're making a contrast with impossible people. And this happens a lot, I think, in the life course literature. You take things like these studies where they look across the life course and they say, if your social origins have been different, like if you've been born rich instead of poor, how would your adult diabetes be different or whatever? So you take someone who has a trajectory like low, medium, high, right? And you're matching them to that adult life course value for their SES. And you're saying, what if I had flipped their early life status, right? You create this trajectory, high, medium, high, that can't exist in my example. Now you might say in real data, there are people who start out high SES and then they fall and then they become high again. But people with non-monotonic SES trajectories tend to be unusual in other ways that make them bad substitutes. Like a lot of people fall in SES because they're sick. Like they're not sick because they fell in SES. They fell in SES because they're sick. They have chronic illness or some other kind of problem that, using them as a substitute for what would have happened to other people isn't a really good substitution either. All right, but let me go back to the selection bias issue. So I set that up as a case control study so that you wouldn't have to worry about the time at which things happened, right? So it didn't really matter when someone became a case and when they fell out of the population, because I just counted up my cases at the end, and I picked my controls at the beginning. So when events happened, throughout the life course, wasn't a problem for me. But now let's think about it in a cohort setting where every time a death occurs, that person is gone from the population, which is probably the more realistic way that we would analyze this kind of data, where we have a cohort of people that we define, and as time goes on, there are fewer and fewer of them, because as they die, there are only the people who haven't died yet still in the cohort. If I randomize at baseline, say I have the opportunity to randomize all your social exposures at baseline. So I know at baseline you're an assistant professor, you're starting out, and I don't want this to be confounded by, say, smoking. So I randomly assign my assistant professors to be smokers or non-smokers, so I know that I have no confounding at baseline. The minute that I have some event, someone dies, they're gone from the cohort, and then I go on to the next moment of time to do the analysis again. But I'm conditioning, to go on to the next moment of time, I'm conditioning on the fact that you didn't die, right? And what happens, what did we decide about selection bias? What happens when we condition on the child of two variables that are independent in the source population? We create a dependency between those two variables in one stratum of the common child. Right? So among the people who didn't die, there is now a correlation between smoking and low occupational grade, even though I'd randomized it at the beginning of the cohort. So because of the randomized design, you're completely unconfounded at the first moment. As soon as someone dies, you're confounded again. Right? So this selection bias in cohorts turns out to be a huge problem. Right? You can think of it as some relative exhaustion of the susceptible people in the population. There's some people who are going to get disease because they're only assistant professors. You know how hard it is to be an assistant professor. You don't last very long like that. And there's some people who are going to die because they're smokers or whatever. So those people who are susceptible to those things get harvested out of the population. And then the people at time 2 are the people selected to be relatively immune to those things. So you end up with an increasingly robust population over time. And this has been actually explored as one of the explanations for like the age race crossover for mortality as well. Like as there's a black deficit for life expectancy, but after you reach a certain age, then they flip, and life expectancy for blacks is higher than whites. So this is another place where this kind of selection bias mechanism comes into play. So if you think you can set this up as a model, as a counterfactual model where you know the outcome for every person. You say, let's take 3 time periods here, and I can say these are all the possible trajectories. There's people who would die at time 1 if they were low grade, and they would die at time 1 if they were high grade. But then there's people who, if they were low grade, they would die at time 1, but being high grade buys them a little bit of extra life. Right? It's good for them, so they get to die at time 2. And then if it's really good for them, they get to die at time 3, but eventually everybody has to die. So time 3 is the latest you can die. And then these are the other possibilities. You were going to die at time 2, but exposure to high occupation extended your life to time 3. So assuming that being a full professor is better than being an assistant professor, these are all the possible combinations. These are the only things that can happen. And right, so it's monotonic. Exposure is only to high grade is only good for you. Right? It can never be bad for you. So when you go through, these are the different, I'll call these A, B, C, D, E, and F. And we don't know. The population must be made of some proportion of these things, and these proportions have to add up to 1. Right? So we don't know what those proportions are, but we know that PA plus PB plus PC, et cetera, equals 100%. So if we go through and figure this out, there's a nice paper by Flanders and Klein that works through this algebra. We find out that the risk difference at time 1 is the proportion of B's plus the proportion of C's. Right? That's actually that proportion of the population that has that pattern is going to be the observed risk difference at time 1. So that's beautiful. Like that's nice. That works out that way. But the really amazing and terrifying thing is what it is at time 2, which isn't that obvious intuitively, but it's worked out, as I say, in the Flanders and Klein article. And if you go through, it turns out to be the proportion of F's minus the proportion of B's. And that's the really amazing and perplexing aspect of this, because this is a difference instead of a plus. Right? Remember, this is an exposure, being, say, assistant professor instead of full professor, that can only be bad for you. Right? It can only make you die sooner. And yet, at time 2, you can get a positive number here if there's more F's than B's, and you can get a negative number here if there's more B's than F's. So you can have as your causal estimate either a value saying that being a full professor is good for you, or a value saying that being a full professor is bad for you, even though we set this up so that it can really only be good for you to be a full professor. Right? So you get this result that can go on the opposite side of the null because of the selection bias. This is exactly what I claim is going on in the obesity paradox example, where you look among the people who have heart failure and it looks like obesity is good for them. I think that obesity is never good for anybody, but because of the selection, you've flipped the sign of this effect. Right? And I think this is an underappreciated problem in life course studies or other kind of cohort studies where you select out a group of people. In the obesity paradox thing, it's especially confusing because they take a clinical sample. They say, we looked at 1,000 people with heart failure in such and such a hospital. Well, it came from an original population, and it selected out the majority of people who didn't get heart failure. So you end up with this very selected subset, but you didn't see the inception cohort, so it's even more confusing. Yeah, so this is just the citation, the Flanders and Klein article that I mentioned in 2007. So it means that some time-specific estimates, as you go through and each time you estimate these things, some can be on the opposite side of the null, even though the truth is that the effect is monotonic, right? That you have an exposure that can only be bad for you, and you reach some time point at which the effect is on the opposite side of the null, it looks like it's good for you, right? Anytime that the population is increasingly selected over time. So the summary here, it's almost 3 o'clock, so I should wrap up. When you have exposure or outcome data at multiple time points, there are many possible effect contrasts that can be constructed. So you think about the causal estimate, it's very hard to be clear about exactly what thing you think that you're contrasting, right? So the causal estimate is always if I did one thing versus I did the other. You have to think about in a longitudinal setting, like a life course study, what is it that I think that I'm doing to people here to make this contrast? So you read these articles, they're like, oh yeah, we found the effect of living in a walkable neighborhood is such and such. You know, like what is it that you're doing there? When are you doing that to people? For how long are you doing it? To which group of people are you doing it? It's very unclear from the usual context. So you have to be clear about this because there's a number of different estimates you could get. And so you want to know which one is the right one. So you have to think about the hypothetical intervention you have in mind. This gets to like if these recent articles by Sandro Galea about consequential epidemiology that matters for the real world, it fits in well with that, thinking about the hypothetical intervention you had in mind. Right? So it doesn't really make sense to study things like, you know, the effect of education in adults unless you had some way that you were thinking about changing the education distribution. You could think about some specific program that does change the education distribution. If I change the Pell Grant formula or something, I will change the distribution of achieved education. But if I take a group of adults and I say, oh, this is the effect of education. This is the risk that they would have had if they were college graduates. Like, how are you going to get all those people to get through college? Like, it's not really clear what you mean by that estimate. So unless you have a specific intervention, it makes it very ambiguous to talk about which is the right answer and which is the wrong answer. Some contrasts are not supported by the observed data. This is the positivity problem I described before, where you can create some contrast. Statistically, you can create some contrast with things where if you looked in the data, you see there's actually no people there. There can't be any people there. You've defined it in such a way so they can't exist. There's a nice paper about this, Michael Oakes called the structural confounding. Structural because it creates, or no, did you call it structural? Yeah, I think that was his word, structural confounding. They did this paper on segregation where they had black and white neighborhoods, like based on the proportion of residents in the neighborhood by race, and they had the SES of the neighborhood, and they found the effect of the racial segregation controlling for SES. And the model spit out the number, like they got the effect, the adjusted effect. When we look in the data, in fact, there were no, in their data set in North Carolina, there were no rich black neighborhoods or poor white neighborhoods. Like by the way that they had defined it, those cells were empty. And yet they got an effect based on model assumptions of like linearity. So they threw a straight line through empty space and they got a number and they reported that in the journal. But in fact, there were no people there. So it becomes a result that's based on the model instead of based on any data. Some contrasts are not supported, and some involve conditioning that creates additional sources of bias, like this. When you condition on a collider, like I talked about, the child of two parents, we call that collider stratification bias, and that generates an additional source of bias that you have to deal with in some way. Even if valid, right, even if you address the confounding there, some time-specific effect measures are difficult to interpret and may seem counterintuitive. Like when you have an exposure that's only bad for people, but after a certain period of time, the risk differences, the risk ratios are all in the protective direction, right? And that's a real answer in the sense that the people with the factor are really dying at a lower rate than the people without the factor at that later period in time. That is a real aspect of the data. But it's not because that factor is ever good for any individual. It's because of the selection of people. Like the people at every time period are changing. Like there was just this paper, this Olshansky paper that came out last year about the fact that for women now, life expectancy is actually, for poor women, life expectancy is actually going down. This is the first period of time, and no, it was women without a high school education. The life expectancy was actually decreasing, right? And it was such a misleading result to report because, they started at like 1940 when 80% of women didn't have a high school education. And they ended in like 2005 or something when, 90% of women did have a high school education. So it's to be a woman without high school education is a much more highly selected characteristic now than it was in 1940. And so you're dealing with a smaller and smaller group of people that have much more concentrated pathology, social pathology of one kind or another, right? Because it's much harder to end up in that category. So to say that the life expectancy of a group of people is falling is misleading, because there's not any group of people whose life expectancy is falling. It's just a worse and worse group to be in over time. That's a very similar kind of phenomenon to the selection bias that I'm talking about. OK, the last point is just that these DAGs are devices for simplifying our world so that we can communicate assumptions to each other. But then we write papers as though these are true. So science always develops these simple models to aid in discovery. We make up these models of things like, oh, I have this model of an electron. It's this ball that rotates around this other ball. Or the invisible hand in economics, the species concept. Like, there's no species. Like, you know, species are supposed to be things that within the species they can breed and make fertile offspring. But like, they have species of, like, you know, viruses and things like that. Like, you know, there's species of things that don't fit this model whatsoever. It doesn't make any sense. The gene concept, we don't know what genes are. Like, after all this time talking about genes, nobody can actually define what's in a gene and what's not in a gene. So these things exist as simplified versions of reality to help us communicate simple ideas, but we shouldn't be lulled into thinking that they have reality. So we play with these things as toys, but the real world is always considerably more complicated. All right, it's 3 o'clock. I'm not allowed to talk anymore. Thank you.
We have time for a few questions, so you can hopefully stay longer.
No questions is always a sign that it was either really good or really bad.
Really a lot.
There's one in the back.
Yes? So this might be the obvious question, but so if we can't take truth from these models, what do we do, right? If our goal is to try to pinpoint causality or explain a phenomenon, and the strategies that we use aren't sufficient, do you have any?
I mean, that's a question about the philosophy of science. Like, I'm not a philosopher, so I can't answer that question broadly. I mean, you know, these tools exist as a way of communicating our assumptions to other people, as a compact way of saying, I'm assuming that my variables are related in this way, and these ones, you know, their error terms have no correlation, and this one is not affected by this one, so they're independent. Like, I'm communicating to you a set of assumptions. You can disagree with those and say, no, I think you're wrong. I would draw it this way. And we can argue about those assumptions and come up with different estimates. And then there's some process of developing consensus between our different approaches so that eventually I start to convince more people than you convince. And then the world starts to, you know, agree with me instead of with you. And that's how science proceeds, I think. Like, so it's always imperfect. We're always making some assumptions. And then premised on those assumptions, we say, this is the answer I would get if my assumptions were right. And then people come along and criticize my assumptions and say, well, this one is not exactly right. You have to relax this. And I have some new data that shows that your assumption was wrong here. And if you change it, this is how much it changes. So we have to be humble about admitting that we're basing them on assumptions. We have to be willing to have people criticize us. But probably the most important thing that we can do in terms of the social process of science, of making it proceed in a healthy way, is to make our data available so that other people can analyze our data using other assumptions so that there can be replication. It's people like Nurses Health Study and people like that who grab hold of their data and don't let other people play with it that are the biggest hindrance to science, because they say, oh, the number is 3.7, and you just have to believe us. You know, we adjusted for certain things, we picked a certain model, and that's just the way it is. And you don't have access to the data, so you can't see if it would work out the same some other way. So I think the most important thing as part of the social process is to share our data, share our code, and let other people analyze it the way that they think makes more sense. And then we can argue about whether there's a difference between those numbers. And then if there is a difference, which one is right? Yes?
I just add to that too. Miguel Graham was here just last year and gave a nice talk where he.
So everything I said is like old hat. Like,
no, actually, this is much nicer talk. I think you laid the foundation for a lot of things that he kind of glossed over. It's more about the results of his study on actually reevaluating versus health data.
The hormone replacement therapy. Yeah.
One nice thing he's doing is actually writing not just one DAG, but dozens, I think, in fact, maybe 100 or so he said DAGs. He didn't go through and show everyone on the slides, but I think you can do a lot of that sort of sensitivity analysis yourself as an investigator. So even if you, for whatever reason, they work with versus study, and can't release the data publicly, I think that investigators can go and refit those models.
Right. If you're concerned about the sensitivity of your estimates, which you should be, right. But if you hold all the data and you just want to get published in New England and then that number is, you're happy to live with that, then you're not necessarily concerned about the sensitivity that way. So I agree with you that the sincere investigator will be very interested in sensitivity to assumptions. Like you make a whole bunch of assumptions, you have to make a whole bunch of assumptions all along the way. And the sincere investigator is really concerned about how sensitive is my result to that particular assumption? What if I had made a different one? And at the end of the day, you're right, it could generate 100 different DAGs for the different ways that you could have bifurcated at each of those points and made a different decision about how you categorize something, about how you measure something, about what you include in the model, about the model form. There's all kinds of decisions that are buried in there. And unless you give somebody your code, they can't even tell all those decisions that you made. So Miguel actually is a good one. When he publishes a paper, he has like an appendix that has like 100 pages of SAS code, which is actually kind of impossible to go through. But at least it's there. If you really wanted to, you could figure out every single decision that he made. That's a good standard to try to reach.
I had also an actual question about some of your earlier slides where you were talking about basically 100% population. I think it's a point well taken. But statisticians mostly will kind of then grab onto the concept of superpopulation in those cases. I'm just wondering if you have a reason you don't like the superpopulation. I mean, it's definitely much less tangible than a...
That's it. I mean, I think there are many people who, I've had this argument with people, and there's different philosophies about how this should go, but many very reasonable and intelligent people think that it is okay to think about a superpopulation model, and this is one possible realization of that theoretical superpopulation. But the thing about that is you have to realize it's a complete abstraction. Like, to say that there's a superpopulation from which the Framingham study came from, like, it's nothing in our world. Like, it's some complete, like, you're in the level of, like, string theory to think about, like, how are the multiple ways that Framingham could have evolved? Like, it just doesn't mean anything in the real world. So I agree that if you're going to be a frequentist, you have to think about resampling. And if you took 100% sample, you have to think about there being some underlying variability that you're capturing when you think about this as a sample of reality. But because that superpopulation is like just completely made up, it becomes a very abstract way to do statistics. Like philosophically, you can't really ground it in anything in the real world. It's a reasonable model, but it's a model that's very abstract and it doesn't have any, like if you tried to explain it to your grandmother, she would think that you were on drugs. Like it just doesn't mean anything in the real world.
So the chair of our nephrology division gave a talk to us last year, and the title was Reverse Epidemiology, and I was wondering what he meant. His studies were about the survival of kidney transplant among high body mass index people, and he was convincing the data that people who are overweight have better survival. And now I understand the epidemiological basis for the results, but he was also trying to come up with a biological possibility argument for why that would be. So, and I'm thinking a student brought also up in a class this week about the Roshansky observation that life expectancy was falling. Are these mistakes useful for generating hypotheses that otherwise would not explore?
Sure. I mean, these observations are always useful if you interpret them in a helpful way. Like I think this empirical question about the obesity paradox, for example, is interesting because there's a number of ways in which it could be true that if you're heavier, you're more robust in some way, or that being heavier is some marker for severity of disease. So if you have some disease that causes weight loss, like heart failure, the fact that you're fatter in that group means like your disease is not so severe yet. So you're actually using it as a proxy for being healthier within that group. So it's actually capturing, it's a kind of a confounding by, because you're categorizing everybody and saying you have heart failure. But if you looked at everybody's individual ejection fraction or something like that, you might see that there's a wide range of different degrees of disease, and the BMI is becoming a proxy for that underlying disease. So there are ways of thinking about explaining this other than selection bias. And I think we just, in one article that we just wrote, we got criticized by Maria Gleamore about this because she did some simulations showing that the selection would have to be very strong to get as large a reversal as we saw in the data. And she was questioning whether that was physiologically possible. And she proposed this idea that there could be selection bias and also some other kinds of effects that are made up of a combination of this idea that BMI is a proxy for something else, like the degree of the severity of disease, and also perhaps some true physiologic effect, that there may be some person for whom having the extra weight is actually protective for them in some way against some disease that actually operates through wasting. So the truth is probably some mix of those things, and the answer, the way to get to that, I mean, some of it involves physiologic studies and clinical studies where you actually try to figure out this disease process and the different ways, the things that contribute to it. And that, you don't want to just rely on observational techniques there, like epidemiology, to adjust for things. You actually need to understand something more about the physiology. And the other way are the kind of simulations like Maria was using to criticize us, where they put in plausible values for these parameters and showed the range of biases that you could get and had a hard time matching the clinical studies. Like you really had to put in a lot of bias to get as far on the protective side as they got. So that led her to say, you need to mix some other explanation in here. This is not enough by itself. It's part of the explanation, but not the whole explanation. It's interesting because when we wrote a letter on a paper by Canto in JAMA they had a study where they looked at people who survived MI and then their mortality after discharge from the hospital. So they selected out all the people who died before they got to the hospital and the people who died in the hospital. Like you get this very highly selected group. And so we made the same argument. And in that, the letter, when they responded to us, they said, oh, you're arguing that it's reverse epidemiology. And we had never heard that word before. So we had no idea what they were talking about. Like reverse epidemiology. We were like looking that up, trying to figure out what that was. So I'm glad that you came across that as well.
It's Kalantazadeh.
Okay, all right. Excellent.
Well, thank you very much.
Thanks.